Great, thanks so much, Beth. Thank you guys for listening. Thanks very much to the organizers. This has been fantastic so far. I'm looking forward to today. As Beth mentioned, I do not have a background in home visiting. I work on health policy research mostly, so I hope you guys will forgive me for trying to stumble my way through your field a bit. I'm looking forward to the discussion afterwards when you can set me straight. Okay, so I'm interested, as you heard yesterday, in the methods that Don Barry was describing. He uses Bayesian adaptive design, and as he described in cancer, this lets him study questions about what works for whom, right? Which cancer treatments are effective for individuals with different biomarkers on their tumors. And today, I'm wondering if we can pick up where he left off and ask what works for whom in the context of home visiting. So can we identify, as HARC has kind of laid out the mission for us, can we identify which critical components, A, B, C, D, those are the columns here, are necessary to achieve the best outcomes for which types of families? Those are the rows in this figure. And you can see maybe family 1 up there in the top is the type of family that really benefits the most from critical component D, whereas family 2 needs critical components A and C together to get the best outcomes. So the goal of my presentation today is to describe to you a design that I think can answer this type of question, can identify what works for whom in this way, faster and cheaper and more effectively than a standard randomized control trial would let us do. As I already mentioned, this is very much inspired by Dr. Barry's work. I'm sure you guys all gathered yesterday, is a genius, and I'm just tweaking his methods ever so slightly. Okay, so before I dive into the nitty-gritty details of what a Bayesian adaptive design is going to do, I want to first set up a nice straw man for you guys and describe what a standard design would do if it were trying to answer this same type of research question about what works for whom. So let's spend a minute just thinking through what the standard design would look like, and then by contrast, I'll introduce how the Bayesian adaptive design would do things differently. Okay, so let's imagine a study that we're designing together, and the goal of the study is to increase participant engagement. We want to decrease the number of missed visits, say. And there are 5 different ways that we've thought up of potentially doing this. I don't know if you guys can read on the slide, but let's see. Here, the first treatment arm is a control arm, so that's just a business as usual intervention that we're conducting in the usual way. The next column here is treatment number 1. Maybe here we're sending automated text message reminders to families before the visitor arrives. Treatment number 2 is the third column there. Maybe we're sending personalized, kind of behaviorally informed nudge text messages to families. Treatment number 3, that's the fourth column. Maybe we're actually giving folks a phone call to confirm ahead of time. And treatment number 4, maybe we're doing something particularly intensive where we send a text message and give a phone call, something like that. And our goal is to identify which of these different treatments is working best for which types of families. So under a standard design, at baseline, let's say we have 20 families coming into our study. And under a standard design, what we would do is just randomize with equal probability to each of those 5 different arms. So 20 families into 5 arms. You can see that I have 4 families, i.e. 4 blue rectangles, in each arm there. And that's our cohort 1 individuals. Excuse me. Now let's fast forward a few weeks down the road. Say we've observed some preliminary outcomes for this group in cohort 1 for the blue families. And at the same time, we've had some new families, cohort 2 in green, walk into our door. And what's particularly important to remember about this standard design is that when we're randomizing the green families, the cohort 2 families, we're going to ignore all the information that we've learned so far. We're just going to, again, randomize with equal probability and ignore what we've learned already from individuals in cohort 1 about what works for whom. So again, in cohort 2, we're now going to put 4 families into each of the 5 arms, equal randomization probability into each of the 5 arms. Time point 3, we observe more outcomes for cohort 1, we observe a few preliminary outcomes for cohort 2, and we randomize cohort 3 with equal probability to all 5 arms, right? We're not taking advantage of the information that we've learned so far when we're picking our randomization probabilities. All right, let's make that a little smaller so that we can compare the Bayesian adaptive design and how it differs underneath. So under the Bayesian adaptive design, at baseline, we're going to do the exact same thing. We're just going to randomly assign with equal probability those first 20 families to each of the 5 arms. Okay, I'm going to pause here because I think if there's one slide you remember from the whole talk, this is the one to remember. This is really the crux of the matter here. Under the Bayesian adaptive design, at time 1, we've observed some preliminary outcomes. We know whether folks are missing their visits or not, preliminarily for the folks in cohort 1. And we are going to use that information to adapt. We're going to learn as we go. And when we randomize cohort 2, we're going to randomize with higher probability to the arms that look like they are most effective for those individuals. So for example, in this last column here, here we go. Let's say in this last column here, where we're sending both a text message and giving folks a call, that based on this preliminary data from cohort 1, we have reason to believe that that's a really effective strategy for increasing engagement among high needs families. Then in cohort 2, when high needs families walk through our door, we're going to increase the probability of randomizing to that more intensive treatment. And that's why you can see these green cohort 2 families stacking up a little bit higher in this last treatment arm. So that really is the crux of the matter. It doesn't sound like rocket science, but it is, as you will see when I begin to share results, it does have some really big benefits in terms of the type of inference we can make. I'll just restate it one more time. We're gonna kind of play the winner as we go along. And as the study progresses and we begin to get a good sense based on preliminary data of what's working for whom, we're gonna use that information, that preliminary information, to inform our randomization strategy going forward for the next cohorts as they come in the door. You can see that happening even more so in cohort 3 in purple here, because we have even more data, so we have even more confidence in this preliminary information. So we're really going to double down on those last 2 treatment arms. I'll make just a quick side point about a really nice statistical consequence of doing so before I get into the more important substantive consequences of doing so. One statistical advantage of doing this is that you can see that these last 2 arms, which have been shown to be more effective than the other 3, that's why we're randomizing to them with higher probability, they've now got bigger sample sizes in them. So what we've done is we've increased our statistical power to tell the difference between the 2 arms that are most effective. So we can really kind of pick out what could be small differences. Since we have higher power, we can detect smaller effects. We can look at the small differences between the most effective arms, and that's going to let us ultimately pick the very best one of all. So that's a nice statistical advantage. But let's think not about statistics and rather about the families and how this design might benefit them. And to do that, I want to answer 3 questions for you in the next 3 slides. The first question is, if we use a Bayesian adaptive design rather than a standard design, do we see better outcomes for the families who are actually participating in our study? 2, do we make better inferences at the end of the study if we use a Bayesian adaptive design, such that families who are getting an intervention after the study has been completed, such that their outcomes will improve? And then 3rd, can we use this Bayesian adaptive design to learn things more quickly and more cheaply? Okay, result number 1. This has to do with the actual study participants. And what we see is that participants, families participating in a Bayesian adaptive design, the study participants themselves will have better outcomes than had they participated in a standard design. There's a lot going on in the figure, so let me walk you guys through it kind of piece by piece. On the x-axis, you see the effect size, small, medium, and large. The 3 different panels show different sample sizes, small, medium, and large. And then the y-axis is where the action is at. The y-axis shows how much we would expect outcomes to improve for participants, for families participating in a Bayesian adaptive design versus a standard design. So this horizontal line here at 0 shows no difference between the 2 designs, and values north of that horizontal line show improvements in outcomes for families participating in the Bayesian adaptive design. And what you can see is that in all 9 of these scenarios, we're getting better outcomes for folks participating in the Bayesian adaptive design, and sometimes those improvements can be quite large, 60% up there for the red scenario, which is when effect sizes are large. So it depends on the scenario, but sometimes you can get quite impressive improvements in outcomes for folks participating in the Bayesian adaptive design. Result number 2, can we produce better inference at the end of the day? X-axis is the same, the 3 panels are the same. The y-axis is a little different. So to answer this question in a quantitative way, are we producing better evidence or not at the end of the day? What I did was to imagine a scenario where we are designing a new intervention, and we're either going to base our new intervention on evidence created from a Bayesian adaptive design, or we're going to create our new intervention based on evidence from a standard design. And then I'm going to feed families through my new intervention, and I'm going to check their outcomes. And what's shown on the y-axis here is how much improvement we would expect in outcomes for families whose intervention was designed based on evidence from a Bayesian adaptive design versus a standard design. And again, north is good. We want values above the dotted line. And again, we see that that's the case in all 9 of these scenarios. Here we see especially impressive gains when effect sizes are medium. And the intuition for you guys there is that if effect sizes are big enough, then under this metric, the design doesn't actually matter very much. You can get away with just doing a standard design. All right, question number 3. I saved the best for last. This is a very exciting result that I'm excited to share with you guys. So here I want to know, can we learn more quickly what works for whom if we use a Bayesian adaptive design? And the answer turns out to be a resounding yes. So to answer this question, I'm going to give you guys another thought experiment. I'm going to ask you to imagine a year-long intervention. We're enrolling a new cohort every 2 weeks, so that amounts to 26 cohorts total over the course of the year. So imagine that I'm going to compare 2 things. I'm going to compare the quality of evidence produced from a standard design after all 26 cohorts have gone through the study. And I'm going to compare that to evidence from a Bayesian adaptive design after the first cohort of evidence, just 1 out of 26 cohorts. And then I'm going to compare evidence from the standard design after 26 full cohorts to Bayesian adaptive design evidence after just 2 cohorts, and so forth and so on. So on the x-axis here, I have how many cohorts of Bayesian adaptive design evidence do we have? 1, 2, 3, 4, 5, and every time I'm comparing that back to evidence from the standard design after all 26 cohorts have been run. And on the y-axis, I ask, how long does it take using a Bayesian adaptive design to get evidence that's as good, that's a coin flip here at 50%, that's as good as evidence from the standard design after all 26 cohorts have gone through. And what you can see here is that these dotted and solid and dashed lines cross that horizontal line at 50% really, really quickly. All of them have crossed that 50% line by 9 cohorts. And just to be concrete about what that means that no matter what scenario you're in, if you use a Bayesian adaptive design, you will get evidence after just 9 cohorts worth of families have come through your study, as you would have gotten if you had used the standard design for the entire year, for all 26 cohorts. So we are learning really fast what works for whom using this design. And the intuition comes back to something I said earlier. It's that we're doubling down our sample sizes in the arms where we need it most, right? We're learning about the effective treatments rather than wasting our sample size and our power on treatments that don't actually end up working very well at all. Great. So I do want to acknowledge some limitations. We need randomization. We need rolling enrollment, because we have to. If we randomize everybody at once, then there's no chance for adaptation. And we need quickly observable outcomes. So I was thinking about family engagement, for example. I was thinking about missing visits or not, and that's not a Y. That's more of an M. You know, it's more on the causal pathway towards what we're actually hoping to affect. And I think in addition, a limitation that's not on this slide because I didn't really wrap my head around it fully until yesterday's conversation, but I think an additional complexity in this particular field is that we need to be able to define components really clearly, and we need to be able to define types of families really clearly. And I have gotten a very clear impression that this is a messy business indeed, but I'm hopeful that we can nonetheless make use of these methods, because I do think they're pretty exciting. And I think I'll just close by saying that I'm excited about the HARC mission to learn what works for whom and to learn it quickly. And I think these methods have a big piece of the puzzle to play potentially. And I think one reason that they're potentially very valuable here is that they retain the crucial methodological principle of randomization. So they let us go after this interesting research question of what works for whom. They let us learn quickly, but they don't sacrifice methodological principles in doing so. We're going to use randomization, so we're still going to get valid estimates of causal effects, and I think that's really crucial. So I'll close here. There's a reference down here. We wrote this up recently. If you guys want to check it out, it just was published a couple weeks ago. Thank you very much.